Hello, Amitji.
Hello, good evening.
Good evening.
I think we can start, right, Professor?
Yeah. Just only for 1 minute, 2 minutes. Actually, this is a half an hour time there. The people are going to reach their home.
Oh,
So,
great.
so 5 o'clock is ended, and they're going to join. Few more people will going to join in by 10 minutes.
Great, sir. Just give us a cue whenever we are ready to go.
Yeah, please. I'll announce.
Sure thing. Thank you. So Amit, while we are waiting, probably we can have a quick discussion in the chat. So hello everyone. Good evening. I hope you're having a great day. So I just wanted to have a quick check on a couple of things so that we can move ahead with our session in a way that is fruitful to everyone. So first thing, have you ever used Matlab and Simulink before? Or is it going to be the first time you're going to use Matlab and Simulink today? You can drop your answers on the chat window. Great. I see a lot of used and first time. Not Simulink. Okay. Great. So this will help me kind of tune the modules or models that we will be using for people who have used it for the first time or not used it as well. But we won't be dwelling too much onto MATLAB and Simulink as such, but more about how to utilize it.
And just to add to what Akhil said, if you have not used MATLAB or Simulink, that's perfectly fine, right? So the reason why Akhil is asking this is to make sure that we take everyone along. So don't worry if you've not used MATLAB or Simulink.
Thank you for that, Amit. Great to see everyone responding in the chat window.
I think we can start so that they can slowly can join.
Great.
Yeah. Welcome back, everyone. Today with us, Akhil Gopinath ji and Amit Kamath ji is with us. So Akhil is an education technical evangelist at MathWorks and works with the academic institutions in India on the adoption of MathWorks workflow in curriculum and research. He graduated with the MS in Chemical Engineering from IIT Madras in 2019. He specialized in process modeling and simulation, optimization, parameters estimation, and artificial neural networks. He has publications in the field of optimization algorithms, development, and utilization of artificial neural networks in physical systems. Also with us Amit Kamath. He works with academia in India and has been with MathWorks for the past 8 years. He has worked on several teams at MathWorks, including technical support, software development, and now in the academic team. Along with the great set of colleagues, he contributed to build MATLAB applications for image registration and pixel labeling. He also has some expertise with NIFTI images, performance optimization in image processing, and interfacing with OpenCV. His area of interest includes computer vision, software engineering. He earned his bachelor's degree in electrical engineering from NITK Surathkal, a master's degree in electrical engineering from University of Minnesota, and another master's degree in computer science from Georgia Tech University. So, sir, yeah, it is a pleasure with us to great pleasure that you have all accepted our request. Sincere thanks to MathWorks, and I again sincere thanks to Akhil ji and Amit ji who have accepted our invitation and willing to deliver a great lecture in our FTP. So, dear participants, I hope it's a great opportunity for you to experience the experts from industry. And if you have any doubts, as you have many questions are there, you can free to ask them during this today's session and tomorrow session. Thank you, sir. Thank you very much for your acceptance. Sir, you can start. Thank you.
Thank you, sir, for the warm welcome and the introduction. I think you have already mentioned a lot about us. So, well, I just want to add one small thing. We work a lot with faculty, students, and research scholars across India, across different institutions, and we try to ensure, as much as possible, that you find success in using MathWorks products in your research or courses, curriculum, etc., and also while the teaching learning process. Amit, anything you want to add before we begin?
Not particularly. No. The one quick thing I'd like to say is we are here to help you. And so if you have any questions, please do not hesitate to either ask in the chat or the Q&A. Akhil will be doing most of the talking today, and I'll be doing most of the talking tomorrow. So while Akhil's presenting, I'll be tracking the chat and the Q&A window. So please, if you have questions, we'll try our best to address right away. So we'll make this as interactive as possible, because this is online and we are at different places. We'll do our best to make it as useful as possible to you. So hope that's okay. Thank you.
Thank you so much, Amit.
Sir, a small announcement. Dear participants, if you have any question, please try to send to everyone option, not to privately, so that I can only able to see those questions. The panelists may not able to see. So requesting you to please post question to everyone. So that either Amit ji or Akhil ji can able to answer. So I hope you are able to understand, right? Thank you. Sir, please carry on. Thank you.
Yes.
Right.
Sorry.
Thank you,
Thank
sir.
you. Thank you. That's useful. And Akhil, over to you.
Right. Thank you, Amit. And even better, if you can utilize the Q&A portion, that's going to be really good because we can then distinguish between the questions that are coming up. Thank you so much. So with that, let me start. So today we are going to talk a little bit about what is reinforcement learning. We're going to understand about what are different aspects of reinforcement learning. And most importantly, we're going to talk about how we can use reinforcement learning and ensure that it works for our application area. And at the same time, we understand, what are the different ways by which we can apply it. Okay. And we'll be using Matlab and Simulink for that. And let's see if this is something that we can do right off the box, because a lot of us have not used Matlab, or we are first time users of Matlab and Simulink, right? So as Amit mentioned, please do not worry. What we would be doing is something that will not require you to have a prior knowledge of Matlab and Simulink. If you have, that's awesome. If not, it's totally fine. We'll still be able to work it out, right? Great. And at any point of time, as Amit mentioned, if you have any questions, please put it in the Q&A. And after every 15 minutes or so, Amit, you can give me a cue. If there are questions in the Q&A, we will take it out on the voice as well, so that everyone is aware of certain important questions that people will have. Great.
Will do, Akhil. Thanks.
Sure. Thank you so much. With that, let me begin. So this is a video. I'm not quite sure if the audio would be hearable by everyone. Just let me know if it is audible. Aman, is it
Akhil,
audible?
yeah, no, I'm not able to hear the audio.
Right. Unfortunately, I think the teams do not let me do this, but I'll voice through what this is.
Yeah.
So this is a doctor, an Indian doctor, who is performing a surgery known as coronary intervention, and he's doing this in a remote location, right? So he's not in that surgical room; he's away, performing that surgery by using a robot which was built by a company known as Corindus. So what Corindus's robot does is it actually puts in stunts, etc., so that folks who have blockage, etc., can be helped out. Because this is a very accuracy critical, and also any small error can actually end up in a very big, or I would rather say fatal result. This is a very important area where robotics have grown out, and accuracy and simulation especially have found a lot of value in, because without that we won't be able to make it. So here the person is actually telling us how exactly this robot works and what did they do to actually build this robot. Just to fast forward a little bit, because I think a lot of things would not be audible right now. So on the left, you can see, they are testing out the robot real time and prototyping it at the same. So this entire process, if you notice, there is the Simulink and Matlab opened out there. So they have developed this entire robot model and tested it out on Matlab and Simulink environment prior to prototyping and building it, and actually using it on real patient. And the proud moment for us Indians is, this was first tried out by an Indian doctor in India, and that holds a lot of value, because this is one of the key surgeries that is done by the doctors in India, and we know how much time and efforts does it take for doctors to do this, and this robot will ensure that no matter which time the surgery is being conducted, it goes on with 100% accuracy. Great. Awesome. So I have marked the link to this video in the presentation, and we will be sharing this presentation and any other resources that we'll be working on today, so that you can go back and take a look at that, and also work out the different problems that we'll be doing today as well. Great. So that brings us to the agenda for the day. So today we'll be talking a little bit first about what reinforcement learning is, by taking an example of us trying to probably train a puppy. We will then talk about what are the different concepts that comes out in reinforcement learning. Then we'll jump right on to how to solve our reinforcement learning problems, and to figure out why, solving that problem, how actually RL works. And then we'll talk about certain of RL algorithms, which we call agents. We'll take an example, which we will do all together, of a very simple system, just to showcase how the implementation process goes on. Then we'll show you an example of a real life problem which was done and solved using reinforcement learning. And last but not the least, we have to figure out whether we have to use reinforcement learning or not, right? And also we have to figure out how exactly can we get started with reinforcement learning, because we all may not be familiar with reinforcement learning before today, right? So if that is the case, how can you ramp up and ensure that you are able to apply reinforcement learning knowledge in your area of application? So we'll talk about that. So without much ado, let's begin. So first question is teaching a puppy to play catch, a process or a example of reinforcement learning, or is it equivalent to reinforcement learning? Now let's take a quick guess. So how do you train a puppy to kind of play fetch? Fetch is basically when you throw a ball or a stick, it needs to bite it and get it back to you. So how do you think people train a puppy to do this? Can you all, probably try to guess around and give your suggestions on the chat window? Okay, so I see there is giving a reward when he does it right. Reward and punishment. Okay. Giving gift when it can grab. Great. Dog is rewarded every time it fetches. Reward. So I think the common word is reward, and I see a punishment as well. So basically, what we are trying to do is we are trying to tell the dog what is the, or puppy, what is the right action we are expecting out of him, and what is it that is gonna give him a benefit for doing that action or performing that action, right? Great. So is there a single word to describe this process? The process of rewarding the good and kind of punishing the not desired. Uh, it's not feedback. Reinforce. Yes, yes. Reinforce is the right word. We won't say learning as of right now. We'll progressively get to reinforcement learning. But yes, you are reinforcing the puppy with what is good, and you're also reinforcing the puppy with what is bad, so as to ensure that the puppy is doing the good thing more compared to the bad thing. In this case, which is not fetching the stick, right? It's not necessarily bad. I would rather say desired action. Okay, great. Thank you, everyone. So please keep up the spirit and do answer, the questions that may be coming up. There is no right or wrong answer. We are all here to learn. It is just to understand what all we think, right? Great. That in mind, let's take a look at how we make a computer to do things that we want, right? There are actually two ways we make computer do things. One is the traditional programming, where we have some data, we write some program to use that data to get the desired output, right? So in that, the computer will do what we have programmed it to do with the data and get an output out of it. And nowadays, we have all heard of machine learning, deep learning, and you have been hearing that the entire session, right? So I'm not going to dwell much on it. But in machine learning, what we try to do is we try to ensure, instead of us letting the computer know what it has to do, we let the computer learn from the data and the output to figure out how the both are related. This will ensure that when a new set of data comes in, the computer is able to, kind of take appropriate action, right? That's the output, and say what is the correct output. So that's machine learning for us. But what is a gap left here, right? What is a gap left here? So before I go into the gap, I'll just briefly describe the differences between these three. So artificial intelligence is the big bucket wherein we want machines to be able to think for themselves and do some desired task, which is done in an efficient manner, which is with more efficiency and accuracy compared to human beings. Then only it would be useful for us, right? And then in machine learning, we are, which is a subset of artificial intelligence, we are training the computer with some data to perform the desired task. So in this, the system may not be, able to find context of things and do multiple different things, but it will be able to kind of do certain tasks it is trained to do in a very efficient manner. And deep learning is a further subset of machine learning, which is related to the way, the differences in the way that we are gonna, train machine learning and deep learning, and what kind of information is required for us to work with machine learning and deep learning, and what is a fundamental artifact or mathematics behind machine learning and deep learning. So there are subtle differences between the two, but deep learning is considered to be a subset of machine learning. I've mentioned these three, but I have not introduced reinforcement learning yet, right? Now I ask you a question. What happens if you want to make an automated driving system? Okay. So let's assume that the image, this is the image uh, that we are actually seeing right now. Let's assume you are sitting in front of the car and we are the automated driving system. Okay. Our task is to overtake this vehicle in order to go ahead. Otherwise, we are going to go too slow, right? Great. So if we were a machine, how would we make a decision, right? there are two decisions I can make out here. One is to go straight ahead, but what will happen if I go straight ahead? I will probably bang up the car in front of me, which is not a great thing to happen, right? Other than that, what I can do is I can take a left and then take a right, depending on how fast the other vehicle is moving and what is the clarity in front. So if you notice, there is a subtle difference between whatever we talked about previously and in this. I'll give a quick guess, or I'll take a quick answer from everyone. What do you think is the subtle difference between machine learning, deep learning, AI, and what we are talking about right now? Okay, that's a great answer, sequential decision making. So we are talking about how that set of decisions were made. Okay, that's very important. Thank you. Anything else? It need not be anything complex. It can be very simple. Prioritizing. Great. Okay. Do you think interaction with environment? Okay, great. I was about to say that. Thank you so much. So it has come up in the chat, interaction with environment. Yes. So in this, we do not have any data with us already, right? We are getting the data then and there from the environment by interacting with the environment, right? We don't know what exactly is the data beforehand. So that's a difference there, right? Now let us talk with respect to a little bit on how this data actually come into picture. So machine learning is actually the big umbrella under which we have deep learning, reinforcement learning, everything coming up into picture. But there is a subtle difference based on data that we saw right now. Now, machine learning have three types. One is unsupervised learning, supervised learning, and then we call it reinforcement learning because we saw that we require a subset wherein interaction is captured, right? So what is, I'm going to just quickly mention what these are, just to give you a refresher. So unsupervised learning, if this is the data given to me, I don't know what this data belong to, but I see that there is a similarity between this and this object, right? So apparently these two can be clubbed together in a similar category, and this seems to be a totally different thing. But what does these things refer to? I don't know. So that is unsupervised learning, wherein I don't know what the output is, but I try to find a pattern or a similarity or a, in the data and try to find a commonality between the data and cluster them or kind of find a class for them. Great. Now, when it comes to supervised learning, you have data. You know exactly what the input is corresponding to, and you know the output that it is corresponding to. You have complete label of it. For example, in this image, you know these are vehicles. This is road. This is trees. This is the atmosphere. You know that, and you train a machine to kind of find difference between or find the sections where these elements come into picture, right? So you are doing a semantic segmentation, and pixel by pixel you're trying to say, hey, this is a car, this is the road, this is the air, this is the tree, etc., and this is a bridge, right? That's the supervised way of learning, which is quite common, and this is one of the most common way of machine learning that we are all quite familiar with. Now, reinforcement learning, thanks to everyone who mentioned right now, it's based on interaction data. So we do not have data with us already. We are working on a real life environment or a dynamic environment to get the interaction with that and use that interaction data to train our system or machine, right? So as we saw, so it is gonna learn from interaction. So if it is gonna go ahead and hit the car, that's an interaction, and it learned that it should not go ahead if there is a vehicle up there, right? If it goes in the left direction, it will be rewarded. So we are reinforcing that, hey, if you do not bang the car, that is a good thing to do, right? So that's interaction data for you. And now where does deep learning come into picture in all this? So deep learning can be very very easily used in supervised learning, etc. But I'll be focusing on what reinforcement learning is. So I'll be talking about where deep learning comes into picture. Okay. So deep learning is actually used when the system or the environment that we are trying to approximate, or the kind of actions and output that we are trying to correlate, it becomes way too complicated, or it is highly overlapping. At that time, it may be difficult for us to work on with a simpler you know way of defining that reaction or relation. For that, we use deep reinforcement learning or deep neural networks to kind of find an approximate way of representing the system. We'll see what this means. Right now it may be all gibberish, but I guess you got the whole idea that for reinforcement learning we need to understand the environment, and we need to figure out how the environment is interacting with the actions that we are taking. And for that understanding of how that environment and action correlation is, we need a some sort of function to that use, right? And that function, if it is too complicated, we prefer using deep learning. I hope that makes sense. So I guess that gets us to our first question here. Are there any questions in the Q&A, Amit?
There isn't, Akhil, at the moment. Just a quick clarification from my side too.
Yeah.
So in the figure, the way you've shown it, so deep learning can be applied to all three of the types of machine learning, right?
Yes.
It can be applied to unsupervised as well, supervised also. But you
Correct.
are going to focus only on the reinforcement learning part today.
Absolutely. Yes. I believe everyone have done unsupervised and supervised learning and machine learning and deep learning already, right? So I'm going to focus on the reinforcement learning bit today. Great. Any questions till now? Any doubts? And thank you, Amit, for clearing this.
No, I don't see anything in the chat here or the Q&A. So I think
Okay. Great. So now let's move ahead then. So now let's officially define what reinforcement learning would most probably sound like, right? So it can be termed as a type of machine learning wherein you have an agent which is trying to learn through trial and error, or when it is interacting with the environment, to do the right thing or to make the right actions and decisions so as to get the maximum reward, right? So these are the kind of keywords that we're talking about. Okay. Now let's imagine a robot, bipedal robot, which is similar to us, right? Human beings, two legs, and we are trying to make it walk on a straight line. Okay. For simplicity, we assume that this particular robot has a hip joint, a knee joint, and an ankle joint, which allows it to move and go forward. Great. Now, one approach to make sure that this robot walks properly in a straight line is basically to do certain measurements, do a state estimation, generate the trajectory of how the joints are and how the body would be moving ahead, and then ensure that there is a control aspect associated to it so that it is following the generated trajectory properly. And based on that, we have to control the motors to ensure that the robot is actually walking on a straight line and not falling down, etc. The problem in this case is it may become way too complicated because of the number of possible parameters and number of possible states that we have to work with, right? So one way to do this is this, and another way, or a conventional way that I mentioned right now. Apart from that, the alternate way is to use reinforcement learning based controller. So what we are doing is we are kind of compacting all the three aspects of this, which is understanding what is the current state, deciding how to move the legs in order to ensure that it is not falling down, and to give the motors its required torques to maintain that motion. This three thing actually club down into one single RL based controller. Our today's focus would be to make this example till the end. Okay, we will be making our own bipedal robot. We'll be trying to see how we can define a RL based controller to ensure that it is walking, or it is at least learning to walk, right? So we'll be talking based on this requirement, how or what all things are required for us to do this. Okay, great. Now, before that, first question comes up is, why should I even care about reinforcement learning? I already have machine learning, deep learning, which is fairly doing things, and I have control systems, PID controls and model predictive controls and other control systems to effectively work with my system, right? So let me show you a couple of examples where reinforcement learning have actually interacted with systems similar to what human beings would be doing. For example, this is AlphaZero, a gaming AI, which is based on reinforcement learning. So in 2020, it was able to beat or become the world champion of computer chess, right? And in in recent times, if I'm not right, if I'm not wrong, before that, it was able to also beat a world champion in Dota 2, which is a very massive multiplayer online game, right? So what this tells us is reinforcement learning can be applied to systems which traditionally may not be easy for a machine to work with, because for a chess game it may be very difficult to kind of work out where exactly or what exact moves to be made and what sequence of moves need to be made, etc., right? There may be a counter argument saying that, hey, we know that what box the chess pieces are, what pieces are there, etc. So that's what Stockfish was relying on, the massive data, so that it can do all the sort of computation required to play the chess. But still, it was not able to win because it was only focusing on a single instance. And whereas we saw that reinforcement learning or reinforcement actually is a process which gives a lot of importance to the sequence on how the actions are being made, right? Great. And to give a further incentive, reinforcement learning is actually gaining a lot of momentum. Unfortunately, the data is actually till 2018, but if you can go to Google Analytics, you will find that reinforcement learning has kind of grown, further as and when we are going to a little bit of human interaction into picture of artificial intelligence, right? Great. So this is a robotic arm example where a robot arm is kind of trying to, match whatever goal we are giving it on the right side. And the robot arm with multiple joints and multiple degrees of freedom is actually doing that. And here we already saw a robot is walking on a straight line, right? Initially, it will not. We'll take a look at this too. Great. So whole thing is, no matter how complex the system is, how complex the decision making is, a reinforcement learning may be able to help you out to ease out that process and to kind of capture the complexity which is in the system. Okay, great. With that, we have kind of introduced ourselves to reinforcement learning. So before I go ahead, any questions or queries?
Akhil, there's an interesting question which goes, can we apply RL to non-stationary signals like EEG for a classification problem? Do you have thoughts on that?
Right, that's a very interesting question. My first thought would be uh, classification is not a dynamic process in itself, right? And if you're considering that, okay, here are two things. One is, what do you want to do with that EEG? Well, is it like you have to classify whether the person is going into a different state of, sinus rhythm or heartbeat systems, right? Reinforcement learning on one side is kind of learning from what is the right reward it is getting, right? So you cannot reward a system uh, in this case in a proper format. I don't know what would be the reward, whether the classification is right or wrong, because then that becomes a supervised learning, right?
Right.
So you will have to think of three things, or we will be talking about the different aspects we need for reinforcement learning, and you will figure out that we need a couple of things to ensure, reinforcement learning is applicable to the system. So I hope that gives you a little bit of clarity. I think while we go ahead, we can give a little bit more emphasis on that. It is not only about streaming data, it is about what is the problem at hand. If the problem is, a system needs to perform a desirable action, right? That may be somewhere, that may be a suitable system for reinforcement learning. Whereas classification is more about the system needs to find difference in this in the input and decide which one is right or wrong, or which one is which category it belongs to, right? And in order to tell what category it is, you have to kind of give information to the system that this is right, this is wrong, right? That makes it more like a supervised learning, not a reinforcement learning. I hope you find that subtle difference there. Great. Yeah, that's a that's a very good question. How RL is different from an optimization problem? I would rather say optimization is the heart of this as well, because we are trying to optimize our system, that is reinforcement learning agent, to I'm sorry, I have not introduced the word agent yet, but let's say that reinforcement learning system that we have developed to make the decision which will give us the maximum reward, which is an optimization problem, right? The only difference is I think optimization in a generic context would be more with respect to the physical system itself, or what kind of a outcome that we are expecting. But in this case, it's an indirect optimization. Physiological signals, denoising physiological signals. Then again, the question comes up: what is the reward you're going to give the system, right? If you can define a reward that can be given to the reinforcement learning system to kind of learn things, then yes. So before we go into that aspect of whether we can use RL for denoising signals or classification, let's take a look at what kind of application or what kind of requirements are there for reinforcement learning. Probably that will answer a little bit more. Okay, Nikhil, I will park your question on what are the proper action items to the next section, because there I will be talking about it. Okay. Thank you so much, everyone. Great questions. Please keep them coming. Cool. So next part. So we have been talking about a lot of reinforcement learning. So there are a couple of words that I want to introduce you. We'll be talking about what these words are shortly. But before that, I want to introduce you to these words. Okay. It's state, agent, action, policy, environment, rewards. These are kind of requirements that a reinforcement learning problem have, right? You need to have states, you need to have agents, you need to have actions, you need to decide on a policy, you need to have an environment, you have to define a reward. But what does this all mean? So to understand this, let me take us back to how reinforcement learning works. We know that it works through trial and error by interacting with the environment. So let's take an analogous example to our pet puppy, right? So when we wanted to train a puppy, our agent is actually the puppy, or I would rather say the puppy's brain, but let's call it as the puppy. Okay. We are trying to train the puppy. Great. That becomes our agent. Now the puppy is going to interact with the surrounding that it has, right? The park. Maybe you're making it play in a park or something, garden, right? That is the environment and what it is looking at. Maybe the images it is getting from the eyes, it would be the observations, right? So whatever it is getting from the environment, these are the observations, or whatever it is being, it is being inflected on, I guess. Now, what is happening is in this environment, we are also present, and what we do actually makes as an observation here. Now, the observation for puppy is that I am having something in my hand, kind of like a stick, and I'm trying to throw it away. Okay, that is the observation it is making. It doesn't know what to do with that stick or what to do with this observation. Okay, as of right now. Now, The puppy, because it doesn't know what to do, it says, okay, let me try something. So it just, instead of going to the stick, it comes to the person and starts wagging the tail or something, right? So that is the action it took for this particular observation. Great. Now, is this what we wanted, right? So this is not what we wanted, correct? So what we do is okay, before I go there, the decision it took, right? It processed in its brain, correct? It took that decision in the brain. So that is a policy, equivalent to a policy in reinforcement learning. Okay. So the policy is something which understands the observation and then takes appropriate action. Okay. Initially, if the policy is there, it's a blank policy. It can do any random action. It need not be right or wrong, correct? So what defines whether it is right or wrong? The reward, right? Now, if the dog comes up to the owner rather than going and catching that or fetching that stick, it may not, it may not be rewarded. And on the contrary, if it goes and fetches the stick, it will be given a treat, right? And that is the reward. So there needs to be a quantifiable reward in order to make sure that the puppy is learning the right thing and not doing the undesired thing. Correct? Now, the entire process that in puppy's case, it is growing its brain. The brain is developing for the puppy. Neurons are being generated for the puppy so that it is learning the correlation between the observation and actions, which will give it, which will end up or result in treat for it. So how does our agent actually do that? That's where reinforcement learning algorithm comes into picture. So the reinforcement learning algorithm, what it will do is, based on the reward and the observations, it is gonna update the policy in order to ensure that we get maximum reward for any observation that it is learning for. Okay, so that's what the reinforcement learning algorithm would do. So are we clear till now? Any questions or anything that is confusing? Please let me know, because this is important for us to move ahead. So on a scale of 1 to 10, how clear is it? 10 being crystal clear and 1 being not at all clear. Can you put your, okay, 11. Okay, that's very on. That's very kind of you. Thank you. Okay, so there is a question. Can we use RL in conjunction with Kalman filters in estimation problems? We'll come to that in the later point. So when we will do the problems, you will figure out how it can be actually worked in this. Okay, so what exactly agents will observe? Okay, the agent in this case, if this was the puppy's brain, it is observing that the person is throwing something in its garden or somewhere, right? That's the observation it is making. I hope that clears it.
Akhil, is it fair to say also that the agent is observing the environment itself? Like whatever's happening in the environment are kind of signals for the agent. Is that fair to say?
Right. So I wouldn't say whatever is happening in the environment, because we need. So the point is, environment may be shared by a lot of different things, right? So what we are focusing on is what is important to us. For example, for what is important to us, that what is happening in the environment is throwing of the stick. That is the new thing that's happening, right? So
Yeah.
that's the observation that we are making. And as we take up few more examples in the upcoming slides, you will figure out why I am not saying whatever happens in the environment, because then it would actually limit us significantly, and we don't want to limit ourselves, right? Yes, there will be a coding portion as well.
Thanks.
Great. So without much ado, I'll go ahead. Amit, are you saying something? I'm sorry.
No, I just said thank you.
Okay, thank you so much. Great. Now, with that in mind, what happens while the training is happening, right? So when the reinforcement learning training is happening, the agent is trying to learn the best policy, which kind of understands what is the current state of the environment, takes appropriate actions according to it, which will result in some sort of reward. It may be positive, it may be negative, based on how well the policy is trained and how well the state action correlation have been learned. Okay, great. And this entire process is done or repeatedly done by a trial and error, which is kind of directed by the reinforcement learning algorithm. Right? This is what we have understood till now. Now, once your policy is completely learned, or policy is actually giving you good rewards or the best rewards that you have set it for, then actually you don't need the reinforcement learning algorithm anymore. You can directly use the policy because it will be able to detect what state is and what actions needed to be taken for that state, because it is already giving us best rewards possible, right? So this is where the final leg of reinforcement learning comes into picture, wherein you have made the policy which is working for your system. Now this policy may not improve with time, so there is a caveat to that. So just keep it at keep it at the back of your mind, because I believe there is going to be a question on this later. Okay, great. Now let's take an example of the self-learning car that we were talking about, right? So I'll ask questions, right? So in that case, wherein our car wanted to, evade through the traffic and ensure that I'm comfortable and I reach my destination in a quick manner, what do you think is the agent? So this is the pop quiz kind of thing. So can you tell me what is the agent? What would be the agent in terms of a self-driving car? Right, the car or the controller in the car, it can be, right? Computers or the vehicle's computer, whatever is the brain of that car. Great, that is the agent. Now, what do you think is the what do we say, environment or observation? Let's talk about observation first. What is observation? So what observation? Speed, direction, traffic, right? It can be anything, right? It can be anything of that sort from sensor reading. So it can be images from a camera about the traffic. It can be readings from a lidar. It can be anything. So it can contain traffic lights. It can contain roads and vehicles, etc., etc. Right? But that actually is the environment also, right? The environment will contain what are the road conditions, what are the vehicle positions, and the sensors are getting this information from the environment to the agent. Okay, so that becomes agent, state, and environment. Now three of them are done. So what is the action? What do you think is the action? Driving, where to drive, brake, accelerator, when to stop. Okay, so action is gonna be, braking, steering, throttle commands. Great, amazing. Everyone, you are already, getting good at reinforcement learning. That's amazing. Thank you. Now, one thing that we need to understand is, because we are going to train the agent, how do we reinforce good things, or how do we reinforce uh, the actions that is desired? What is the thing that is required? Reward, right? Great. What do you think is the reward in this case? Apart from not crashing the car, okay, destination is not a reward, right? No scratch on the vehicle. Yep, that's possibly a reward. Or quickness, best possible speed. Do you think least fuel consumption can be a reward? Safe driving, yes. So this is where you have to decide what is the major thing that the agent should look at. Whether it is to ensure that there is no scratch on the vehicle, or whether to ensure that it is driving at the best possible speed, or is it to decide passenger safety and comfort? So this is where you have to decide that. So that is, oh, sorry. that is policy. I have already mentioned that. So that is what the reward would do. Okay. I'm pretty sure policy is quite clear, so it's okay. So reward is going to be decided by you. So in this case, our reward is to optimize the comfort of the driver and the improve and improve the fuel efficiency. Okay, or get the best fuel efficiency. Great. And now we will have a reinforcement learning algorithm to use this information and kind of do a trial and error while interacting with the environment, and to ensure we get a policy which gives us comfortable driving with maximum fuel efficiency. Okay. So once our policy is completely trained, then we don't need the reinforcement learning algorithm. We can directly have the policy which is able to map the state and the action, and is able to take actions for any given state based on whatever information the state is giving it from the sensors, which is getting the information from the environment. So finally, we can say this policy is optimizing the driver comfort and fuel efficiency. So you understand that there was a question regarding whether it is quite different from optimization or quite similar. So you understand that in this case, it's quite similar to optimization, but here I am not sure if the classic optimization will work.
Akhil, there's a good question at this point. It says,
Okay.
at which point can we consider the model to be fully trained?
Oh,
Is
that's a
there
great
some
question. That's a great question. So, okay, the whole idea is, what is the maximum reward that you expect, the system to gain when in the training phase? So the fun part is, I don't know. It can be anything, because for the system that you have, the reward as much as you can get, that is a good reward or a good train, right? Okay, thanks, Amit. I was getting a message regarding breaking of voice. Is Amit, is my audio breaking by any chance?
it's all right to me, Akhil. Maybe it's a network issue. So we
Oh, okay.
um,
Right. Thank you.
yeah, thanks.
Right. So practically, is it possible to reach at the state of no need to update the policy? See, the whole thing is, this entire thing is an approximation. So where all it will work and what are the outliers where it will not work is something that we always are not sure of, right? It's all based on statistics and probability. So the whole thing is, you cannot know what reward is the best reward possible unless and until you have kind of like defined number of actions and states, that can happen. If it is discrete and you know what is the correct action to each of the states, yes, you can have 100% accuracy and reward for that. But most of the real life problems are not like that, right? Most of the problems are quite open ended. So reward is something which is to be decided by you based on what is the kind of confidence you want for the system, right? If let's say, for a self-driving car, if the reward of 500 that I have set up is sounding to be too good, then that may be my cutoff. So in order to understand a little bit more about this, I'll walk you through an example where you would be solving such problem and telling me what exactly happens. Okay, great. Now, with that in mind, I think we have talked about what may be the last leg to deployment of these reinforcement learning policies onto real life problems. Okay. Now, I think we are about to complete our 1 hour, so I'm going to be a little bit quick on certain things. Okay. So in order to figure out what learning is basically, we understood that we are trying to map uh, correlation between observations or states and actions via a policy, right? And that policy is nothing but a function which contains a lot of tunable parameters. And what we are trying to do is, we are trying to tune these parameters in order to find that suitable actions which would give us the best possible reward. Okay. That's the whole fundamental background of what we are trying to do mathematically. Okay, great. So this is the standard definition that you can put up for this. Now, policies, how do we represent this? I mentioned functions, right? So in certain cases, when there are set number of states or observations and set number of actions, you can also use a lookup table to kind of simply represent what is the policy for this observation, do this action, for this observation, do this action. For example, if if the clothes have, let's say, mud stains, then use water and a little bit of detergent. If the clothes have ink stains, use water and detergent plus some sort of removing agent. So these are kind of discrete problems wherein you can create lookup tables to work with. Now, if it is continuous problems, right? For example, setting of temperature for your, optimum temperature for your microwave oven. So at that point of time, your temperature is a continuous system. You have continuous states by which you can, tune your microwave oven probably by a dial. So there, it may be possible to represent those kind of policies by a polynomial, right? But now if it is a very complicated system wherein you have input or observations in terms of images, you have observation in terms of sensors, signals, you have observations in terms of any other XYZ, device, then that becomes a complicated system. And that's where deep learning or deep neural network would come into picture, and it will be able to help you map these observations with the actions. So that becomes the policy. And this is actually quite complicated, complex. This is a policy for complex systems. And more often than not, we try to not work in this unless and until totally necessary, because this becomes a little bit of a black box for us to figure out what's happening, right? Though this gives us a very good efficiency. So there is always a give and take policy in all of these, right? Great. Now with that out of picture, I think we are on the last leg of our intro portion, which is how do I set up and solve a reinforcement learning problem, right? So for that, we have to define the reinforcement learning workflow, which states that first we have to understand what is the environment and we have to define it. Once we have the understanding of the environment, we need reward, right? We have to define what is the reward that the environment is going to get or give out to our agent, using which we will be able to train our agent, right? Then we have to decide on how we are going to represent our policy, whether it is going to be a lookup table, whether it is going to be a polynomial, whether it is going to be a deep learning neural net, oh, sorry, deep neural network. So we have to decide that based on what is the observation, what are the states, etc. Right? Then we have to define the reinforcement learning algorithm or the agent to actually train this particular policy and to ensure that the policy is able to map everything properly. Right? Now, finally, we get to the training process where we are doing or making the agent do the hard work and ensure that the policy is actually able to map the observations and the actions. Last but not the least, just by having a policy doesn't matter, right? That policy need to be put in real life system to be useful. And that's where deployment portion comes into picture. So we'll be taking a quick look into how we can deploy things also, so that we have a complete understanding of how end-to-end problem solving actually helps us to deal with real world problems and in a very effective format. Okay. Now, taking up the example of walking robot, we would be doing this, wherein our objective would be to control the walking of this robot so that it walks on a straight line. But before I go there, I have to tell you certain steps we have to perform for reinforcement learning, which is creating the environment, defining the reward, and providing a state input, and to decide the agent, right? So because this is going to be a little bit difficult, so I'm just going to show you what happens usually. So when the training starts, it actually is falling down. And finally, what we want is it should be walking something similar to this. Okay. Before we go into that, I want you to understand how this training actually works. Because if you get this, then no problem, whichever problem that you have, whether it is robot, whether it is, process control, whether it is any other XYZ thing, you will be able to do that. Okay, so let's get a detour into how actually reinforcement learning training works. And I'll need your help in this. Okay, so now let's assume that our agent in this particular example is this red circle. Okay, and our objective is actually to reach this blue square. Okay, now the environment that we are considering is this grid of 5 by 5, right? 5 by 5 rows and columns. Great. Now the state is defined as the square in which our red circle is in. Okay, right now the state is 1 comma 4. That means it's in the first column, fourth row. Okay, cool. Now the action is it can either go up, either can go it can go forward, it can go backwards, it can go up, it can go down. Okay, these are the 4 actions it can take. Great. Now the reward is, so what I have decided is I wanted to reach this particular circle in the quickest format, but also with the maximum reward point. Okay, and there is this blockage out here. That means from here it cannot move, or there is no path here. Okay, so the only possible squares it can go to are the grayish squares out here. So for every movement it makes, because I want to ensure that it is getting to this particular square in the least possible movements, I'm going to penalize every movement it takes with a -1. Okay, but the only movement where I have given a little bit of advantage to it is the special square out here, which I call as teleportation square. So what happens up over here is if it reaches to this square, it actually teleports the circle to this particular square. And because this is going to bring it close to the reward point, I have rewarded it with a +5 score when it reaches this square. Okay, and finally when it reaches our objective square, it will get a +10. Okay, now before I go ahead, is this clear? Is the problem clear? Great, awesome.
Akhil, just to clarify, you can't go out of the grid, right? Like in the current
Yes,
state, you can't go left.
right. So my
Because
environment is my environment is constrained to this block system, grid world. So anything beyond is termination. We don't exist there. Okay. So it is not possible to go out of the grid. Okay. So I think something is not clear. So I'll explain it again. Our agent is this red circle. The environment is the grid world, 5x5 grid world. State is the square in which the red circle is in. Action is either it can go forward, either it can go back, it can go up, it can go down, or we can say right, left, up, down. Okay. And right now it is at 4-1. So that means it's in fourth row, first column. Okay. And the reward is every step it takes, it will get -1 because I wanted to reach our 5,5 or this blue box in the quickest format. So every step it takes, it penalized so that it takes less steps. Correct. Now every step, oh sorry, when it comes to this block, it is a surprise block where it will get +5 as the reward point. Okay. And when it reaches the objective, it will get +10. Awesome. Great. Now, can you tell me what is the shortest or what is the maximum reward it can obtain? I'll give you 5 minutes. Please, everyone, compute at your end. What is the maximum reward it can get? Please don't worry of being right or wrong. We are going to understand how it is going to compute. Okay. So you tell me what is the maximum reward it can get. Okay. So let me see. So I have a 13, I have a 12, I have a 15, I have a 8, I have 4, I have 13, a lot of it. Great. And I have a couple of coordinates as well. So 1, 4, 4, 4, uh, then 5, 2, 2, 5, 1. Okay. Great. So we have a very detailed answer as well. Okay, let's do this ourselves. Okay, let's try to compute this. Now, when it, I think we all are agreeing to the fact that this is the shortest path, right? Either it can go here and here, or it can go here and here, right? Let me kind of use the features that I have up over here. Either it can go through this way, jump from here and then go here, or it can jump through here and go here, correct? These are the this is the shortest path. And there is another path that some may consider, which is this one. So I'm going to kind of change the color for that if possible. Okay, no problem. I think I'm not able to change the color, but no worries. Okay, I have erased that and I'm going to use a different color. Awesome. Okay, great. Now let's compute the scores. Okay, when it comes up over here, it's -1. For jumping another one, it's -1. For jumping up over here, it gets +5, right? And then we have -1 for here and +10 here. So how much is it? So it comes to be -1 for jumping here, -1 for jumping here, +5 for coming up over here. That's 3, -1. That's for 2 plus 10. That's 12. So I compute 12. Awesome. Great. So we have a lot of fails. Let's see if it is right or wrong. It's been quite some time that I have done this. So let me also try it out. So apparently, these are the possible actions it can take, right? This is the possible actions it can take. And what it took is, in between, suddenly it took this, okay, if this is for me to tell you how exactly reinforcement learning is working, okay? So initially, these are the possible steps it can take, all the possible actions it can take. Now, when the training was happening, it luckily had one of the paths taken by it like this, okay? Now, what it actually came to understand is coming to this particular square and coming to this particular or moving right in this particular square actually gives it a lot of reward, +5 here and +10 here. So what is gonna happen is the RL agent is gonna ensure that the policy is gonna remember these two steps. Okay, so it is gonna give weightage to these two steps. Now after that, it is gonna kind of come to the final or the best possible path that it can take when our circle is in this particular square, starting from this particular square, right? And when we compute it, I think it is coming to +11 points. So we missed out on -1 somewhere. I think we missed out on -1 up over here because there is a -1 for jumping from this to this square, right? And then we get a +5. Cool. So for +12, everyone alongside with me, don't worry, you are pretty close. For everyone who mentioned 11, that's amazing. And Parul, yes, you're right. Great. So now you understand how it worked, right? Now let me ask you, what if instead of, okay, what if instead of having -1 for every movement, what if I was giving -2? Let us go back now. In this case, let me erase everything. What if instead of -1 out here, for every step, I give -2? What do you think is the shortest path now, or the path with best reward? So let's see. -2, -4, -6, +5, that is -1, -3, +10, that is 7. Great. Now let's see this. -2, -4, -6, -8, minus 10, and 0. Right. Now, let me ask you one more thing. What if instead of uh, you know, plus 5, what if I was giving plus 1? That's it, plus 1. So let's see. So minus 1, minus 2, minus 4, minus 6, that is minus 5, minus 7, plus 10, that is minus, so that's 3, right? So now the reward is decreasing. There is a possibility that it may take some other path as well. So what I want to highlight up over here is your reward designation plays a very important role in defining how or what action on state correlation the policy is learning. So this is one of the most important aspect of reinforcement learning, that is to define what is the reward that you're going to work with. Okay, I hope that makes it clear to everyone.
Akhil, just a quick question.
Yep.
The individual moves that there are, right? The reward for that is negative. The example that you gave.
Right, correct.
What if it's 0? What would be the maximum reward that someone would get?
Then that would be plus 15, right? Because then what happens is the most rewarding action can be anything. It can go through here, 0, 0,
Right.
0, 0, 0, 5,
Right.
0, 10.
Right.
Then it will be 15. So there is no optimal path to it. So then it will be only focusing on how to reach this particular point.
Well, then there's no, I guess what I was trying to get to is that there is no limit to the reward it will get, right? So if it's 0, it can just go to that plus 5 block. And then in fact, instead of jumping to the plus 10, it can go back in reverse and then do the plus 5 again, over and over and over again. So
Yeah,
essentially, it
yeah,
can
yeah.
be
That is
infinite.
also possible. That is also possible. Yeah. See, that's exactly what happened in one of the trial games of AlphaGo.
Mhm.
So they tried it out with a game in which there is a simulation of environment, creation of world going on. It was like a Minesweep game or Minecraft, if I'm not wrong. And what happened is the algorithm did something totally different than what it was supposed to, and that was scary. So this is a similar thing that happened to that Facebook's chatbots. Two chatbots were talking to each other, right? They ended up creating a language of their own to talk.
Yep.
So yes, thank you so much for bringing it, Amit. So what Amit is saying is, if I give 0 for every step, then what happens is it can take this step plus 5 instead of going to plus 10. It can go up over here, take a round plus 5 plus 10, another round plus 5 plus 15, and so on and so forth. So there's a possible way of getting even better rewards than we would actually get by directly going into blue box. So there's a possibility that it will never actually go into the blue box. It may start looping around. Right? That's a fantastic observation. I hope that makes sense to everyone. Great. Now, I hope you all understand and accept that reward is something that we have to be very careful about. Otherwise, our system can go in directions we may not even be expecting or thinking of. Right? Great. So we have done this. Now, the question is, what if we had a different path, right? Would the same set of or same path be our best choice? Not necessary, right? It's not necessary. It all depends on rewards again and what is the shortest path. So the point is now the path would be different. Instead of going through this path, it now can directly jump to 10. It's a possibility, right? Or it can either go here and then try to come back and jump to 10, whichever. So it all depends on what exactly is it trying to do. Great. And how you have set up the reward and the system or the environment. Great. Now in this case, because we only had limited amount of possible states, that is 21, because 4 of these are like not possible states. So we have possible we have encountered all the possible states and all the possible actions that we can take, and then actually decide on what actions are best. So no matter where you start, you can actually map how exact step or what exact directions you have to take in order to get the best. So this is what the policy may look like. Now, based on all the rewards it has computed by trial and error, it has come up and derived a policy out of it saying, hey, this is the policy. The policy will say if my initial position is this, the policy says go right, then either go down or go right, and then take the proper action. So that's it. The whole thing is this particular derivation. This is a kind of reinforcement learning wherein we are deriving the policy from the reward, cumulative reward that we are getting. Okay, best cumulative rewards. Now, what if instead of this 5 by 5 grid, I'm using this grid? So how easy or difficult is it? Do you think it is doable in this right now manually, or even by a system processor? Do you think it is a simpler task to perform? Anyone? Do you think it would be easy for us to solve this similar kind of problem here? No, right? It's complicated. It has no limited number of states. It's a lot of states, and based on that, there is infinite possible combinations. Infinite being a very large number in this case, right? Great. So how do we do this? That's where before I go there, this is kind of similar problem that engineers and scientists also have, because most of the problems that we work on usually have so many state space and so many possible combinations that we have to work with. For example, this small robot arm, which has if I'm not wrong, 6 joints, it has approximately 3 trillion states that it can assume. So you understand how complicated the things become, right? And that's where, or this is example of lidar. I'm so sorry. So this is an example of lidar where the image is coming in and there are so many different data coming in. So it also has to deal with so many different states. So that's where we actually come with deep learning or deep neural network into picture. Because if the system is too complicated, we may need to approximate certain portions, and we may need to kind of work with it as a system simultaneously rather than working on it state by state. So let me take an example to show what happens. Okay, so what would you do now? Let me ask you this question and probably take it forward. So you have 3 states: S1, S2, and S3. You're starting from S0. Which one will you take? So if I tell you that you're going to get rewarded 5 points for the first one, 10 points for the second one, and 40 points for the third one, which one will you take? You will take A3, correct? And now for going to S4, you have again 3 paths, right? Now the reward for that is 100, 50, and -10. Now the question comes up: will you take the same path? Will you take A3 and B3, or will you take some other path now? Now I'm sure that you will say A1, B1, right? Why? Because A1, B1 is giving you the best long-term reward, right? And we call this reward in terms of Q or quality. Okay, the quality that we are getting, or the quality of reward, long-term reward we are getting from A1, B1 is 105, which is quite good compared to the other two, right? That's the best. So the logic is, now you decided it based on the rewards, what you're getting, and based on the long-term reward, you're kind of getting the system to take that route. Now how did this happen, right? Because reinforcement learning at the start, it does not know the reward of each of these states, right? So that's where the training comes into picture. So the training, what it will do is it will do certain trial and error, and it will get certain rewards and understand from that what exactly is needed or what exactly is the best reward. So for a deep neural network, let's assume the network actually resembles the same state. it can actually have weights associated, or the weights may be associative of what A1, A2, and A3's rewards are, right? And based on that, it can find out the Q values, and based on that, it will tell you what is the best path. And how does it do that? The Q value is updated for long-term estimation. We use something known as Bellman equation, which actually is a recursive equation or recursive formula, which kind of gives weightage to the previous state and the next state that is actually giving the best reward. So don't worry about this equation. This is just for our awareness that this is the equation which you will quite often come across if you are going to work on uh, reinforcement learning algorithm development, right? Not application of reinforcement learning, but more on algorithm development. You may come across with this. It is it comes up in lot of different types of RL algorithms like Q learning, DQ, and DTPG, etc. Okay, so we'll talk about a little bit on this. Now, with that in mind, I think now you understand how the reinforcement learning works and what the training is, right? So before I go into certain more and put everything in a coding format and try to solve a real world problem, is everything clear till now? Is there any confusion in any part? Anyone? Great. So if you have any questions, please feel free to drop it in the chat or the Q&A panel. Amit will, help answer the maximum queries that he can. If there are something that is left, we can take it up in the voice too. Great. Now with that in mind, let's come to our major attraction, that is agents. And I'm not talking about James Bond. I'm talking about reinforcement learning agents. Okay. Great. Now, what does this agent do? We have understood that it is responsible for training the policy and contains a reinforcement learning algorithm to direct it properly. Great. So how do we go about these training? Right, that's a question, right? So there are different types of RL algorithms out there, which can be broadly classified into three: value-based, policy-based, and actor-critic. So value-based is something that we're going to talk about, which is an indirect policy representation, wherein that would mean that we are not focused on how the policy is being represented. It is being extracted from the reward value. So what we are doing is we are focusing on how to get the maximum reward and defining a function to capture that action of getting maximum reward and then extracting the policy from it. I will talk about the other two as we move ahead. So we are going to focus on the first one right now. So remember this example. So in this example, what we did is we took all the different actions, we computed all the different Q values or all the different rewards that we have based on all the actions we took, and based on that, we were able to extract a policy for no matter what state we begin with and no matter where we are, right? So that's how the policy was done. So this was a value-based, reinforcement learning, wherein we were only focused because the number of states were very less. We could easily compute the rewards that we will get for moving in any direction, and based on that, we were able to approximate what the policy is going to be like. So this works for problems with limited number of states or discrete number of states, which are quite easy for us to compute. Okay, great. Now policy based, what happens is instead of focusing on the reward or identifying a function for reward, we focus on training the policy. So what we do is we kind of try to train the policy wherein we are trying to map the state and the and the actions. And reward is something that we are taking care of with only focus of maximizing the reward. We are not focused on what is the function for reward and what is the predictability for reward. We are not focused on that. We are only focused on what is the action and this what is observation and what is action to be taken, and to try to maximize the reward based on that. So there is no function for reward in this case. Okay, I think I have already mentioned how this works in policy. Great. Now, there are a lot of different things that comes in policy-based training, like you have to kind of do an optimization. So there are different gradient methods to do that, like gradient ascent method, because we are maximizing the reward, right? So in this, we may not be focusing on all the states, right? But we are only focused on the total expected reward that any state can give or any action can give to the system. So in this case, we are not limited to finite number of states. The states can be infinite and continuous, and we'd still be able to perform or extract the policy out of here. So this is just a generic representation on how the gradient ascent method is actually trying to find the global maximum reward. Okay. So I'm not going to focus on this because this actually brings us to the gambit of our domain of optimization, and I'm pretty sure everyone is quite pro at that right now. Okay, great. Now, one thing that I wanted to actually talk about is exploration and exploitation, because when we are talking about cumulative reward, we have to talk about how much you have to explore or how many unknown states you have to visit, because there is a possibility that in the first state itself you're getting let's say plus 100, or in and that is like a huge state, huge reward. Then should I stop my exploration of states there, or should I go to another state and see if my reward is increasing or not? So there is always a trade-off between these two. Okay, so one is you keep on doing what actually is going to give you the best reward till now based on your current experience. It is like if you are aware of that shop right next to your home. If you are aware of the shop right next to your home that gives you the best ice cream, you tend to go to that shop again and again. You're not ready to explore any other shops because you know that you get the best ice cream there based on your limited amount of knowledge then about the ice cream shops nearby. But what if you are a explorer and you decided, hey, I already get good ice cream here, but I think I can get some better ice cream. So you start exploring then. So you start doing things which you have not done, right? Now it may kind of end up giving you a better reward, or it may kind of end up giving you a bad reward. It it possibly can do any of these things, right? But now you have more information about the states that your system is taking. You have more direction towards which direction the system is not giving me good reward and which direction the system is giving me a better reward. So you have a better idea now. Okay, so pure exploitation, it's go left because I know that I am getting best reward in S1 and just go get it. That is the ice cream. I know I get best ice cream here, just go left. I don't know what is there in S5, S6 and S7. I don't know what ice cream I can get up over here. So I'm just going to focus on the one I know. Now, if it is exploration, exploitation, you're missing out on what may be possible, rewards we get here. It may be possible that S7 has +5, which is way good, right? But we have never explored it. So we are isolating ourselves to the known things. So if you see in this case, we actually got better rewards if we had explored more, right? Now, pure exploration problem, we don't care that we have +1 in this, we are getting good ice cream out here. We are focused on understanding and we believe that if we explore more, we'll get better rewards. And this time we definitely get better rewards. But the problem is excessive exploration means excessive computation, right? Excessive computation means a lot of time for you to train your system, right? So, and you may not know when it will converge, right? Because there is infinite number of states in the problems that we are working on. It is not possible for us to explore every single state, right? So that becomes like, when will the system converge? When will I get the best reward? So, and also because the unknown states can reward negatively also. For example, if it is a case of car, if you keep on exploring, it may be possible that you may end up damaging the car or destroying the car too. So it becomes very dangerous and costly when working with real life hardware. Okay, so we always need a balance between the two, exploration and exploitation. So this is an example for that. I'm not going to take too much time. It's more about how we choose career path. First year, we explore all the topics, and we have no financial returns for that exploration. Then by second year or third year, we kind of become specialized in certain topics, and we kind of see the potential of gaining money with that specialty. Finally, we converge to a specialization where we want to create our career or take as a career path, and that yields us the best financial return. So this is an example of how exploration and exploitation need to be balanced. Okay, great. So what are the pluses and minuses of policy-based and value-based programming, right? So policy-based is this is gradient descent based because it's optimization. We are trying to maximize rewards. It is based on dynamic programming where we are trying to figure out all the different Q values and trying to represent it in terms of a function. It is effective in continuous spaces. It is typically made only for discrete decision spaces, right? Action spaces. Many trials are required for policy based, but this is sample efficient, right? Because we only take set amount of decisions. It can learn probabilistic or stochastic policies, but not here. There is no policy representation, right? We are extracting the policy based on the Q function. So that is where the actor and critic kind of thing comes in picture, which is kind of like best of both worlds. So it learns the policy and at the same time it learns the reward function as well. So it gives a balance between exploring and exploitation. So out here, what happens is there are two neural networks which are simultaneously trained. So I hope you are comfortable with neural networks, right? I think you have had the neural networks, etc., for a lot of time, right? So what happens is the actor is completely focused on learning what is the action it needs to take for the observation. It's more and more focused on that. And critic is focused on, based on the observation and the action that the actor has taken, what is the expected quality or what is the expected reward that I can get. Now, what happens is actor is only focused on, as I mentioned, correlating observation and the actions. Critic is actually focused on ensuring that the value it is predicting for the reward is similar to the value it can get from the environment. Okay. Now the problem is the actor is actually not aware of the reward. Only critic is aware of the reward. And critic makes that prediction on what action is good and what action was not good. And it kind of gives a nudge to the actor to go in the right direction where the observations are taking actions which is giving maximum reward. Okay. Now before that, right? So to simplify this, whatever value that the critic is predicting, this value is predicted reward. It is trying to say, hey, if based on this observation and this action, I am expecting that the reward would be this much. Now we compare that reward, and if the reward and the value are different, then there is an error, right? And that error actually is what is gonna direct the training process of this critic network. Okay. And based on that, the critic is gonna give a feedback to the actor saying, hey, actor, whatever decision you have made, it is not giving a good reward. So now make good actions or good decisions. And this will direct how the actor is being trained. I know this may be a little, dubious right now, but on a scale of 1 to 10, how clear is this? 10 being crystal and 0 or 1 being you are not able to get what's happening right now. Everyone, please, it is important for me to understand if you're getting me in here or not, because this is not a concept that we usually get in one go, right? It is totally fine if you're not able to get it, because I'm here to kind of give you an idea of what this is, because based on this, you will be able to figure out how or when to choose actor or critic system, when not to choose it, and how to build it, etc. Right? Oh, Amit, I think there is a fun question about GAN. So because Amit is going to talk about GANs tomorrow. So Amit, do you want to take that question?
Yeah, it kind of is. There is. We'll talk more about GANs tomorrow, so hopefully it'll be clear. But this whole um, zero sum game kind of tension between the actor and the critic, that's very related to the two networks that are in generative networks, right? Generative adversarial networks, the discriminant and the other one. Yes, it is related, but we'll talk more about it tomorrow.
Great, thank you, Amit. So just to repeat, because I believe there is some sort of not clarity, so I'll just take this example and this diagram for doing this. So actor is trying to find a correlation between the observations and the actions. So actor gets observation, makes and takes some actions. Okay. Now what critic does is it takes a look at the observation, it takes the look at action, and then tries to predict a reward. Okay. And now what happens is the environment is actually giving a reward, actual reward, right? And the critic is actually comparing that actual reward with the one that it predicted. Now, if it is predicted the correct one, then that's awesome. So we don't need to train critic anymore. But if it is different, that means critic needs to change the way it is computing the reward because it is not able to predict it properly. Now, what happens is, actor needs to train itself also, right? So actor needs a feedback. So what actor is getting is whatever is the reward that is being predicted by the critic. Okay. So whatever reward is being predicted by the critic, the actor is going to make its changes. For example, if the critic is predicting that it is going to increase the reward, the actor is going to say, hey, this direction is good, let me tune more in this direction. If the critic predicts that this is going to reduce the cumulative reward, then actor is going to say, hey, that direction is not good, let me stick to the other direction. So that's how the actor is actually improving itself. So if you notice, one key thing to understand is actor is actually never ever in touch with the reward from the environment. So we don't know how exactly the how actor does not know whether its actions have impacted good or bad because the environment is only interacting in terms of reward with critic, right? This reward that is coming from the environment is fed to critic, nothing else, right? So that's the beauty of this. Great. So now what happens is actor and critic actually takes the best of both worlds, and we can actually work with continuous spaces, discrete spaces. We can learn stochastic policies. We are more sample efficient. We don't need to work on completely the entire states, etc. So we are actually taking the best of both worlds and making it into one. So more often than not, for complex systems, you will encounter actor-critic type of reinforcement learning. Great. Now, with that in mind, let's actually quickly jump into the practical aspect of it. In order for you, before we go into the, sorry, apologies, I have a, thank you. I just had a sneeze, sorry. So, in order for us to easily and quickly understand how reinforcement learning works, so I'm going to take a very simple example of a liquid tank. Okay, this is a tank. It may be a water tank at your home, wherein water comes in and you remove the water through an outlet. Correct. The objective of this is to maintain the level of water in the tank. Okay, that's it. And the equation or the model for the tank is this. Now the question first comes up, why do I need a model, right? Or why do I need a equation for this? So now let's actually take a look at the reinforcement learning workflow that we set up, right? So let me kind of close this and I'm going to share my entire screen now. Is my screen completely visible now?
Yes, it is. Okay, we can see your PowerPoint
Okay,
scrolling up and down. Yeah.
great. So you remember all these different aspects, right? Environment, reward, policy, representation, training, deployment. So in this, because we are not having a real life tank at the moment at our hand, we are going to simulate a tank as our environment. Okay. If you have a tank sensor which is giving you the level of liquid in the tank, and also giving you an understanding of what is the flow rate, outlet flow rate, what is the inlet flow rate. Perfect. Then you don't need to simulate the tank. You already have real life data. But because I don't have a real life tank at my hand, I'm going to simulate that environment. Okay. So before without much ado, let me open up MATLAB. So for those who are aware of MATLAB, who are not aware of MATLAB or who have not used MATLAB before, when you open up MATLAB, you end up in this page, which contains a couple of things. I'm just going to quickly show you the certain layout. There is a workspace which contains all the variables we'll be creating. Current folder is kind of directory where all the files or the folder that you are currently working on is. And this is a command window wherein you can type different commands, like let's say a is equal to 10, and you can execute those MATLAB commands. And as you see, the variable is created up over here. So that being that, so to learn more about MATLAB, you can always go here and say learn MATLAB. At the end, I will also share further resources for you to get started with MATLAB if you have not tried it out before. Okay. Now, first thing first, because my system is a water tank system and it is a dynamic system, I'm going to create it in something known as Simulink. So Simulink is a graphical environment for designing dynamic systems and simulating them. Okay, so it is a non-code based but more of a flowchart based environment. So here we are going to create the system that we have wanted to simulate. Okay, so the system that we want to simulate is, if I'm not wrong, this is the portion, right? So I'm going to copy this thing image and I'm going to paste it out here. Okay, great. So as you see, this is a more like a flow chart. This is a canvas where I can create my system, right? So in order to create this or make this particular equation in Simulink, what I need is blocks, and the blocks that I need is up over here in the library browser. So when I click on it, I can see a lot of blocks are there, like commonly used blocks, mathematical, discrete. There are also blocks which is quite relevant to physical systems. For example, I have Simscape blocks, multi-body blocks, belts, conveyors. I have electrical blocks, various controls, electromagnetic, motors, etc. And fluid. Even I have moist air, fluid, isothermal liquids, a lot of things, right? So what I need out here is I need an integration block because I want to integrate, right? That's what my differential equation is actually telling me. So there is an integrator block. What you can do is, one way to add this block is you can just drag and drop this in the canvas and the block will pop up in the canvas. That is one way to do this. Okay. Now I have an integrator. So what am I integrating? I'm integrating the rate of change of height. And what am I getting after integration? I'm getting height h, right? This is what I'm getting. Now the thing is, these red lines are nothing because we have not connected anything out here yet. So what we need is we have to create this equation out here, right? So first thing is I need an input volumetric flow rate V, correct? So assume that it is a constant for the moment. So I'm going to say constant. And that is going to be coming up over here. And I'm going to rename it and say this is V. I'm going to say it is a unit flow rate. Okay. Now this, so what are we going to do here? We are going to create this equation in a flowchart format. Okay. So V needs to be multiplied by V and divided by A, correct? So what I'm going to do is I'm going to use something known as gain, which I'm going to say it needs to be multiplied by B and divided by A. Please don't worry if you're not able to figure out what the syntaxes are, because this is just for demonstrating how to build system in Simulink. There is an entire learning course for Simulink, which is 2 hours long, which will make you comfortable with Simulink in the go. But I hope the logic is quite clear already, so don't worry about that. Okay. So we have B by A into V. So we are getting V from here. I'm just going to name the signals because it is easy for me to figure out what's happening, right? So B by A into V. So this is what is coming out of this block. Great. Now I have to subtract it with A root of H, correct? H is already here. I have to find a square root of it. So I'm going to say sqrt. It is going to give me square root of h. Now I have to multiply the square root of h with a. So I'm going to say gain a. So that's here. Okay. And that is a by a, correct? Great. I've gotten a by a. Great. Awesome. Now what I need is I need to subtract these two signals, right? So subtract, I'm going to subtract b by a v minus a by a root h. Great. Now this is what is equivalent to dh by dt. So all I have to do is connect these two together. Great. And that's it. So I have replicated and created my equation out here without having to write a single line of code, right? Now there might be red highlights out here. That's because I have not defined these variables, right? So I have actually, there is something which is already created out here for this. So let me take up. So I've created this already. Right. So there is water tank. So it is internal model. So you can actually get it. So this is the system. So right now it is PID, but I'm going to control this, right? So what it is doing is same system, right? That we created. There is volumetric flow rate B by A. It is getting subtracted with H root, root of H into A by A getting subtracted, and we are integrating that to get the H. That's it. This is the same model that we created, right? Now our objective is right now it is being controlled by using PID controllers for desired water level. Let me show you how it works. Okay, so you get PID controllers and everything as a part of this. So when I run this, so what is happening is Simulink at the back end is numerically integrating and solving this ODE and giving us a solution. And that's where the magic happens. So whatever you manually write for numerical integration or numerical solving of ODEs, Simulink is automating that task because we are more focused on applying that skills to solve problems, right? So if you see out here, right now we are using ODE 4.5, which is based on Rangikuta fourth and fifth order method, right? And this is a variable step solver. And that's where we are getting the solution. So you can see, you can explore this solution. Okay, great. Now what we can also do is we can set the time for which I want to simulate the system for from here. Right now it's simulating for 200 units of time. I can say 50 units of time and then simulate it again and get the results out. Okay, great. And I get this. Awesome. So now this is my environment, right? The water tank system. So I'm going to remove everything else. For the moment, I'm going to save this as save a copy of this. I'm going to save water tank copy, and it is going to be in my sorry, it's going to be in the folder that I have created for today, single tank. Great. So I have a copy of this. Awesome. Now I'm going to remove this. I'm going to remove this. Okay, this is copyrighted. So there it is. That is my environment. What is my environment giving me? It is taking volumetric flow rate, and giving me the height of the liquid in the tank. Awesome. Now, what is my objective? I have to maintain the height of the liquid in there, right? So what I've done is I have created something like this up over here. This is internally available, and you can actually, use this. So here is a step-by-step, procedure on how to do this. Okay, this is the model that we had. You can always open it up. Now the steps are we removed all of this, right? What we want is we want to create a reinforcement learning agent instead of PID controller. So for that, we have to create what? First of all, we have the environment. That's great. Now what we want is, so before I delete, I think I deleted the reference variable also, right? I need the reference variable at this. So I'm just going to remove this. So this is my environment. I've connected this. I have to create and connect all of this. First is reward. Okay. So I'm saying define the reward. So I'm going to use Notepad to show you what the reward might be. Okay. So what do you think would be the reward? Let's take a quick guess. When should I give a positive reward? This is my error. Let me term is this is my error. When should I give a positive reward? Can you give me an answer to that? When the error is low. Okay. So when the error is low, I should give a positive reward. Okay, less than threshold. What should be the threshold? Let's say I'm saying the threshold is this. Okay. So error if error is less than 0.1, then or 0.01, then reward plus 10. Does this work okay? Does this sound okay? Great. Now, when should I penalize this? Because obviously there need to be some penalty because there might be wrong steps too, right? So what should be the penalty? So every single time step when it is having error greater than 0.01, do you think that would be a good penalty, -1 for that? So I'm going to say if the error is greater than or equal to 0.01, then reward -1. That is penalty. You can decide on your reward. I'm just formulating on a general aspect. Okay. Now my tank has a limit, right? My tank should not be empty or go below 0. And my tank should not overflow as well, right? So if that is the case, what I have to do is I have to penalize it if the tank overflows. So if H is greater than or greater than 20, let's say my tank holds 20 meters of water in height. Okay. If H is greater than 20, then -100, because that is a strict no. I don't want it to ever go there, right? And if H is less than 0, then also -100, because I don't want it to, kind of empty my tank completely, correct? Great. So that is the kind of condition I have to put up. Awesome. So this is my reward. I have defined my reward now. And in rewards, okay, these are my rewards. And you can easily create this in here by using simple mathematical blocks from the library browser. Considering we are running short on time, so I'm going to just open up a model where I have put up this reward. Okay. And it may look like, let me open it up. Sorry. Okay. So it may look something like this. Before I do that, let me actually open the system. So don't worry about this. I'm going to give you all these models and everything. So I have created a reward out here. So the reward is, this is when error is less than, error can be positive or negative, right? So I'm going to take an absolute value of it. If the error is less than 0.1, in this case, I've taken 0.1 and not 0.01. If it is less than 0.1, then give it a benefit of 10. And this is not, if it is not less than 0.01, then give it -1. Okay. That is now added. These two reward points are added because we want cumulative reward. Correct. Great. So now the point is, let's come back. Now this is for my height, right? So what I have done is, because I need to stop my simulation ever if my simulation is actually giving me like, the height is less than or equal to 0, which is physically not possible, right? So that means there is some sort of error that is happening in my, reinforcement learning calculations, which is not right, and that is not exactly how the policy should be mapping. So what I've done is I've taken height if it is greater than or equal to 20 or less than or equal to 0. That is a condition. Okay. Then give a reward of -100. Okay. Now sum it all up. That becomes your cumulative reward. Okay. Is this clear? Everyone, on a scale of 1 to 10, how unclear is this? If you can tell me 10 being very crystal clear. Can you quickly put it up, because we are running out of time and I do want to ensure that we are getting to a point where we can implement this on our own. Okay. Okay, so I get a 3 also. So just a quick question. Is this
Akhil,
portion?
sorry, just to interrupt. I think some people in the audience are trying to run this along with you on their own as well. This is my guess. If that's the case,
Okay.
you may find this to be a little fast. So
Right.
I suggest please watching what Akhil does and then running it on your own later on. Akhil, does that work?
Yes, thank you, Amit. Right, it would be really helpful if you can, focus on the actions that I'm doing right now, because I will be sharing all these demos, all these step-by-step instructions and everything to you, along with other resources. So you don't have to worry about it. And at any point of time, if you face any problem when you're trying it out, please, you feel free to contact us, and I will be there to support you, and my team is also there to support you. So don't worry about that. So right now, maybe we can just focus on what's happening right in front of us, and then we can take a look at it on the later stage, right? I hope that makes sense.
Yep, thanks.
Great, awesome. So out here, what is happening is, if the absolute of error, because errors can be if you add certain things, errors can go negative and positive, right? If the height is going above and below the required level. So at that time, what we do is we take an absolute of that value and ensure that that is less than 0.1. If it is less than 0.1, then I get plus 10 as my reward. If it is not less than 0.1, that would mean it is greater than 0.1. Then I get -1 as reward. And if it is exceeding the bounds, that is less than or equal to 0 and greater than or equal to 20, then I get -100 as my reward. Is this clear now? Great, awesome. Now the point is, now I have my reward set up. Great. Now that reward is set up. Now what I need is connect this reward and get this thing moving around, right? This is my reward. I have created a small block for it. You can always create blocks for yourself by just selecting all the blocks that you have and going to modeling, or sorry, multiple, and you can say create subsystem. Okay, that's how you create that block. Anyways, that is Simulink more of it, but let me show you what it is. Okay, now I have created the reward. I hope this is visible now. Great. So this is my reward, and this is when the simulation should stop, because I know that level should not be exceeded by this. Now the point is, I need to show in my observation. What are the observations that I need? One is, what is the current height? Correct. That is an observation. What is the current height? What is the error? That is also an observation. And what is the cumulative error till now is another observation. And we integrate that, right? If we integrate the error, we get cumulative error. And uh, these three become my observation. So what this black box, which is known as mux, is doing is, it's just combining these three into a vector of 3 elements. One is integrated error, second one is error, and third one is height. Okay, keep the sequence in mind because this is very important. First one is integrated error, second is error, and third one is height. Okay, that becomes my observation. So these are the states that the reinforcement learning agent is going to get. Okay, so this is my reinforcement learning agent. You can get this from here. There is a reinforcement learning portion. You can actually get it from there. Reinforcement learning RL agent. Okay, awesome. Now you have connected everything. Awesome. And the action that it will take is the flow rate of water that is going into the tank. That's it. Is this setup clear? Everyone, it will take me approximately 15 more minutes. Is it okay if I take 15 more minutes? Please do let me know. Otherwise, the recording is also there. You can take a look at it later on. Thank you so much. So I will continue then. Professor, is it okay?
Yes, sir. If the participants are happy, there are no issues.
Great. Thank you so much. Great. So we have a reinforcement learning agent. We have set it up. So I hope this is clear to everyone. If this is not clear, please do let me know. Now, what do we need to do after this is my agent is put up over here, but I haven't defined what type of policy I'm going to use. I haven't decided on what is the kind of reinforcement learning algorithm I'm going to apply, etc. Right? That is something that is still missing. So this is only our environment and how the environment is interacting with the agent. So this becomes very clear because we can visually see what is happening, correct? Now what we need is we have to define the agent. And to do that, there are two ways to do that. Okay. One is you can use Matlab script or coding to do this, which is what I have done up over here. I will walk you through this and then show you an easier way of doing this as well. Okay. Easier way, but a limited way, because easier is not always the most open way for you to work with, right? So out here, what I'm doing is I'm just defining two things. One is I have to let my agent know what is the number of observations I'm making, correct? So what this tells is, hey, my reinforcement learning has a continuous numerical specification, which means it's a continuous input of three elements, which means there are three observations that I'm going to work with together. And each of these observations have a lower and upper limit, which is given by this minus infinity, 0, infinity, infinity, infinity. So if you remember, the observation one was integrated error, second was error, and third was height. And even if, because we were using absolute, sorry, we are not using absolute error here, right? So it can be minus infinity as well. Great. So I hope this is clear. So this is telling the configuration of your observation. And now I'm just going to name this variable by saying, hey, this is observations for me. Okay. This specification corresponds to observations. And I'm giving a description so that anyone who is going to work on this is able to understand what these 3,1 mean. So that means integrated error, error, and measured height. Now everyone knows that, right? So the number of observations I'm making is the first dimension. That is 3. Great. Now similarly, I have to define action, correct? Action is what? How many actions are there? Just one, because we are controlling the flow rate. So I'm saying that action is also a continuous output with only one action to be taken. And the name of the, this variable is given to be flow so that it is easy to understand which is observation and which is action. And the dimension of it is 1. Okay. Right. Measured height can go to infinity because, it is open, unbounded, but it can't go below 0. But if it goes anywhere above 20, well, let's assume that the policy is suddenly estimating that the height is, let's say 1,000. That means the policy is not actually predicting the right height. And that would mean that the simulation first need to end. 2, it needs to be penalized. 3, the policy needs to be updated. Correct? So that's why my infinity, because we are not going to limit our policy right here. We want it to be generic. Correct? Great. Now this comes into picture. Awesome. Now I have defined observations. I have defined actions. Great. I'm running this. Now I have to build the environment. Okay. So I'm saying the environment is in my Simulink model, which I have created already. RL water tank is the name of the model. Let me open it up for you. So name of the model is RL water tank. Great. And the agent in that tank is named RL water tank space agent. This is RL agent, which is a part of this RL water tank model. Great. And the observation and the actor info is already given, which is defined by observation info, actor info. That's it. Okay. I prefer doing steps till this in Matlab because it is quite easy and straightforward to work with. Now, beyond this, there will be two possible ways of working on it. Okay, so I'm going to show you the first way, which is by coding format, which is saying specify at what time your reward should be computed, which is every second or every unit time the reward should be sampled, and the system should be simulated only for 200 units of time. Okay, this is something for reproducibility, so that whenever you are also running this script, you will also get the same result, so the random numbers are all same. Okay, so that you can also verify the results and get the same results that I am working on. Okay, great. Now this is the area where it becomes a little messy, because here we have to create our actor and critic neural networks, right? Now this is a coding way of doing this. Another way, which is more, I believe, which is more elegant way of doing this, is via application, which is here in MATLAB. We have a lot of applications to help you work, on MATLAB and Simulink with use different application areas without having to do much of coding. One of such application is Deep Network Designer. So what it provides you is with a graphical user interface to design your neural networks. Okay, so it is similar to what we have been doing in Simulink, dragging and dropping blocks. So instead of dragging and dropping blocks in this case, we would be dragging and dropping and connecting our neural network. Okay, so it will take a little bit of time because a lot of things are open from my end, right? So let me see, my deep neural network should come up somewhere here. Sorry, here is, oh, here it is. Great. So I'm going to start a blank network, but if you are interested in doing some deep learning related workflows and you need to do or use some pre-existing networks, you can also get those from here and work on it, like AlexNet, VGG, and all that. Right. So this gives you a flexible environment to visualize and then work on your network designing portion. So I'm going to create a blank network, and you can see I can create the network by dragging and dropping, layers out here. For example, in this, I'm going to have a feature layer. I'm going to have a fully connected layer. I'm then going to have a ReLU layer. So I'm sure that you would have learned about these layers in your deep learning workshops. So I'm not going to go deep into this, but I'm just going to show how to create these networks using Deep Network Designer. So all you need to do is connect them, and you would, kind of create your network. Now, if you want to analyze whether you have created your network properly or not, or if some parameters are mismatching, you can always click on analyze, and it will give you, uh, you know, the deep network design analyzer. So it shows me that there is a error here because I'm missing an output layer, because all the output need to be coming out through an output layer, right? So that's what it is giving me an error. So this is very good when you're working with complex networks as well, because you can easily create, connect, and also change the parameters, right up over here. And if you're working with images, you can always import your data right away and train it in this environment itself interactively. So you don't even have to go to MATLAB for that. So you can import the data from the data pane, you can import the data, and you can start training as well. So this is right now possible for image data. So just in case if you're interested, you can take a look at that. For our means and purposes, I think I have shown you what Deep Network Designer is. And once you have designed this, designed your networks, you can always export it. You can export it as a code, or you can export it as an object so that you can use it. Okay. So for the moment, I'm going to stick to my MATLAB script because I've already written this. So it is going to create a critic network out here. And similarly, I believe I will create an actor network. Okay, great. So this is what my critic network looks like. This is visualization of my critic network. And here I'm setting the options for my critic network. I'm saying how fast or slow it will learn by changing the learning rate, what is the gradient threshold, what device to use, whether GPU or CPU, etc. Right? Great. Now here I'm going to define my reinforcement learning algorithm. I'm going to say the critic network is a part of RLQ value representation, because critic is going to learn the or estimate the reward values, right? So that is the Q value. So it is defining that. So what I'm trying to show you right now is this is a code-based workflow. Okay. So there is going to be a lot of errors because I have not run this. And then I have to run this sequentially. So you have to run this sequentially so that all the options are always used. Okay. Great. So I don't have a GPU. That's the whole thing. I only have a CPU. So I'm going to change it to CPU. If you have GPUs, you can use GPUs. I only have a CPU right now. So it is not going to work for me right now in this system. And you can always run for actor network. You could similarly create an actor network to define the options, and you do a lot of the different things, right? TS I have not defined. TS is out here. So the whole thing is you can do this like this, train your network or train your reinforcement learning and create a policy and then get everything out. This is one way of doing this. Because we at MathWorks emphasizes on two things. One is enabling the engineers to kind of find value in using things and increase the productivity of doing things. We always create applications for repetitive tasks which can be applied directly. So one similar task recently came out is or app that recently came out is reinforcement learning designer. So what it does is it automates this process for you and gives you a graphical user interface to work with. Okay. So this is a pretty new one. So here what it gives you is it gives you the option of defining what all different things you're working with. For example, if you're working with environment, you can always say, work with a custom environment. You can create a custom environment and bring it up. For example, if I'm going to say environment, I already have an environment variable in my Matlab, right? I use the first two lines as I mentioned before. As I mentioned before, I love to use these two lines, basically these lines, because this actually gives me a flexibility of defining things much more robustly. Apart from this, I prefer not to code much. So I get here environment and I get that environment out here. Great. Once I get my environment in, I can actually create a new agent. I say create a new agent and the agent's name is agent one. It is to be fit in this environment env. And I'm going to use a DDPG. I'm going to talk about what these algorithms are. And this is the neural network. Okay, you get an option up over here. This is one way of doing that. So once you create the agent, the agent will come up over here. You can select that agent. Its properties would pop up over here. So you can see a lot of options come up, right? So this is the noise model. So somebody was using Kalman filters out here. So whenever you train or you kind of do a reinforcement learning, you always have to account for noises and how to filter those noises, etc. And how to kind of ensure that the gap in the prediction is kind of accounted for, right? The blind area. That's where you can probably work it out, right? So out here, you can have an overview of whatever properties that you have set up. So you see all these properties are something that we set up there, and it is automatically populating up over here. This is the reason why I feel this is a little bit more comfortable to write those two lines in MATLAB and then come up over here. You can select all the options that you want, learning rate, gradient threshold, etc., etc. To define everything. Also, you can import your, networks. So if you create your networks on Deep Network Designer, you already have that in your workspace, right? Because you exported it. Then you can select on it. Let's say actor neural network, you can say actor network. So that's because I have not named it properly. Or critic neural network, you can say critic network. You just have to name it properly, okay? Because it should match with the observations and the name that you have given up over here. It should take observations and it should give out flow. That's the only requirement or ask. Once you've done all of this, you can always simulate your system. So here I'm going to simulate my system. That is a water tank system. and it will show me the simulation results right away, just to check whether your system or environment is actually simulating when you're connecting it with the RL system. So once you've done that, once you have simulated your system and etc., you can always work on this and get things moving around. Okay. So once you have done that, you can actually accept it, saying that, hey, this is correctly simulating, just to have an understanding. If it is not, then you can actually, you know, reject it and redo the simulations by correcting your errors if there are any. Now, once you have done that, you can actually go up over here and say train. Under the train panel, you can train it. The best part, you can change which option to use out here. You can use parallel trainings. You can use parallel systems on your cluster, high performance computing clusters, or you can use Amazon Web Services cluster. You can use any of these clusters easily by these options, right? So what happens is I'm completely bypassing the coding format, because this is more easy and more usable for people who are trying to use reinforcement learning for any workflows. Now, before I go anywhere, so finally, when I have done all of this, so I get a kind of result like this, wherein I'm always getting a proper response. Okay, it's almost overlapping with the actual point. Now, just to showcase a little bit more effectively what we wanted to implement this on, this was our robot problem, right? So I will be sharing this example with you. So I created a bipedal robot out here. So this is an entire script similar to what I have written, I will be sharing for the water tank. This entire script defines everything in detail, what it is, what exactly different things are, what are the reward functions, what papers we have referred for this, etc. So you can get all of this, and you can create using all the different applications I mentioned. Okay. Now, what I wanted to showcase is what happens to my where is my bipedal environment, right? Let me open up MATLAB once again. Out here, if you see, so there is a project out here, that's all. So I'm going to turn or close down other things so that it is a bit faster. Just to showcase what the robot looks like, okay? Let me close this. Let me close everything else. Great. So this is my robot, which I have created using physical blocks, which is like lower leg, upper leg, joints, etc. So if you see, I have not even written equations for those. These are physical blocks, right? So I've created these joints out there. This is by using Simscape multibody. So actually Simulink helps you to create all these physical blocks, also physical models also, so that you do not have to rely on equations alone. You can work on the components that you're comfortable with. For example, if you're an electrical engineer, you can actually work with electrical components, etc. Great. So now here it is, our model. Initially, our robot may not be able to walk. So let me run this example. Okay. Let me run this example one by one. So the beauty of working on such a system is you can visualize the robot when it is walking. So let me take a look at it's opening a parallel pool because I'm working on a parallel system. So what it does is it opens up all the cores in my CPU so that I can parallelly work on it. So this is possible in any system. Even in your system, you can use all the cores in your system automatically. All you have to do is say use parallel. That's it. And you saw how we can change the environment, right? So while this is happening, any questions? Deep Network Designer is application is available in which versions of MATLAB? That's a good question. Please do pose these questions in directed to everyone because this might be a question for all. I believe, if I'm not wrong, it should be there in 2019 onwards. MATLAB R 2019A. Amit, do correct me if I have missed out any versions of there.
Yeah, so Deep Network Designer has been around since 18B.
18B, okay.
There's also another question, Akhil, about evolutionary reinforcement learning. Do you know anything about it? I'm not aware myself.
Um, I'm sorry, I have not heard the term before. Can you give me an idea of what evolutionary RL is? Maybe we have different terminologies for it.
Uh, I do not know either, so maybe you should take that offline and later.
Yeah, I can connect with you later on for that. Great.
Yeah.
So with that in picture, I think, all right, so I'm doing training out here. That's the whole point. Oh, are you mentioning evolutionary optimization algorithms?
I think so, yes.
Oh, right. Okay. Yes, yes. So there are a lot of work going on, wherein the reinforcement learning training process itself is kind of expedited by using evolutionary algorithm, because the whole thing is gradient ascent or gradient related methods may not always work, because if there are multiple optimums out there, there is a possibility you may end up in a local optima rather than going to a global optima, and that will critically dampen the reward that you're getting, right? But using evolutionary algorithms may improve that. But often the case is evolutionary algorithms, usually meta-heuristic algorithms, are used. I believe the most famous one that we have heard of is genetic algorithm and particle swarm algorithms. So these algorithms do work quite well, but they require a lot of iterations compared to you know uh, gradient descent method, etc., or gradient ascent method. So that is a caveat there, but there is significant amount of research going in that area to ensure that with minimum amount of iterations, we are able to reach the global optima and kind of speed up the process of reinforcement learning agent training. And this is also in context to one of the questions that we asked, right? When do we ensure that the policy is completely trained and we no longer train the policy? So there are a lot of researches going on so as to make this algorithm so small enough that it can be deployed with the policy, so that we don't actually end the training of the policy ever. So it becomes ever learning policy, right? So these are particular areas that you may want to explore. I hope that answers your question, Mohammed. Yep, great, awesome. So what is happening right now is it's training vigorously, and I think we will have to end this right now because the training itself, because otherwise it will take a lot of time for us to work on, right? So what I'm going to do is I'm going to just showcase you a trained system because I've already done the training for you. And you can actually click this check mark at any point of time, and you can take a look at how the things are. So let me simulate this. So when I simulate this, you will notice a mechanics explorer kind of thing comes up. So let me take a look at, let me show it to you. So you see out here. So this is the robot that the reinforcement learning is kind of, we trained using reinforcement learning. Right now we are simulating it using the, policy that we have trained. Okay, great. So you see, luckily it is able to walk, but it is kind of limping, not that great, correct? Are you able to see this? Let me fit it into fit to view. Here it is. Sorry, I'm getting this WebEx's buttons on the top, so it is not letting me do much of things. Great. Are you able to see this right now? So what we have to highlight is this robot is actually in Simulink. We are defining the dynamics of this robot in Simulink, and we are using reinforcement learning to control its joint positions and by controlling the motors, right? And we are actually enabling it to walk. But you see, it is walking, it is upright, and it is able to make the distance. But you will see it is not that great walking, correct? So that would mean that whatever rewards I have set up, I need to improve that. Whatever training cycle I have put up, I have to train it further, right? So the beauty of reinforcement learning is if you take this policy and start training again, you will not have to train from scratch. You will actually have an improvement on the training if you have changed the parameters properly, right? So this is the benefit of reinforcement learning up over here. Now to answer a couple of more pressing questions that we got, can I use reinforcement learning for classification? The point is for classification, uh, reinforcement learning may not be used, I believe, to the best of my knowledge, because what is the reward that you're giving? There is no difference between if you already know what is the output that you want to get and then use a deep learning neural network to kind of train it. It becomes a supervised learning itself, right? So I would not call it reinforcement learning. I would rather say deep learning. Okay, so that's one. Second is the most important differentiator where reinforcement learning comes into picture is reinforcement learning is a very very much dependent on the sequential data. So we understand that every step that we take, it actually has an impact on the overall reward point. In certain type of reinforcement learning, it is very important to identify, or next action is always dependent on the previous action. But there are other types of reinforcement learning algorithm based on Markov process, wherein your next actions may not be dependent on the previous one, but your rewards may definitely be, right? Because we are ultimately looking at the cumulative reward. So with that in mind, I know I have been not been able to kind of show you the completeness of this given the time, but I hope you were able to identify all of this together, right? Do let me know if this is not clear. Great. So what we were able to do is we created this environment out here in Matlab and Simulink. So the environment was in Simulink where we created the robot model with legs, arms, sensors, world, etc. Right? So this video actually showcases you all the different things of the robot. You will see these are the observations that we have almost, if I'm not wrong, 38 observations we have, right? And similar amount of action points also. Great. Now we have created the environment. Now next is reward creation. So this actually shows you how the reward has been created. So the reward equation is actually taken from a literature research article, and it has been cited in the script. So you can actually refer to that literature to figure out why they have taken it. Just to give you an idea, it is, rewarding the forward motion. It is penalizing the deviation into y-axis because it should not deviate and wobble here and there, right? And it is also penalizing sudden jumping action, sudden elevation and depression. It may be kind of bouncing also, right? So we are penalizing that, and we are also penalizing for putting over efforts in actually walking, because if you put over efforts, our motors will require more energy, and that is not good for us. So there is a penalty for overly using energy as well. Okay, so that's what we are showing here. And here it shows how the networks were made using the deep network designer. So you can actually follow this if you have any queries. And then we talk about how the architecture was imported out here and how it was put together as the DDPG agent. Okay. It is about the actor network now. Sorry, this is about the critic network now. Then we create the RL agent finally. So once we have the RL agent, we pulled it out. We put the settings. These are the options that we have to set up. And finally, when we start the training, we get something like this, where the robot is falling down. And towards the end, ideally, we should get something which is walking like this. Okay, so this is a video which showcases how the training sequence has worked out for us. Okay, so you can take a look at this later on, but this is something that I wanted to highlight. So these are different types of algorithms or agents that are available in MATLAB, and these agents, all of these are model independent. Even if you do not have model and you have data, like for example, if you do not have robot model, but you have data to work with, you can still work with it. And at the same time, what model free out here means is it is not dependent on what kind of a model you're working with. It is independent of that. It can work with any type of model as well, right? It's model agnostic. Great. What you have to understand is these three are value based, which means they are good for estimating the quality or reward function and then deriving the policy based on that. The reinforce is a policy based, wherein it is trying to estimate the policy and trying to not focus on the value or the rewarded and just focusing on maximizing the reward by gradient ascent method like exploration and exploitation that we talked about, right? Last but not the least, these are actor-critic net, agents that you have like DDPG, A2C, A3C, PPO, etc. And these are all usable for continuous and discrete spaces. When you have continuous observation space or discrete observation space, you can use this. But for action space, we have DDPG, which is working for continuous action space. Otherwise, everything else is for discrete action space. Okay. And you're not limited to this. If you have any idea on creating agents and training loops, you also have the flexibility of creating your own custom agents and training loops. You can connect us and we will work with you on to showing how you can do that. Okay. So after training, we saw how it works. This ours is a little bad compared to this. This one is a little more better. So the observation that we made is we created the policy. Once the policy was trained, now we can use it separately. So the deployment portion comes into picture. So just to wind up, deployment can be done on any target hardware. For example, if this is robot, uh, which is right now commissioned real life, and the robot would have some controllers on the board, right? So this policy would be deployed on those control boards. And the best part is you don't have to worry about these problems or inaccuracies that happens when when you're deploying it, because obviously real life system and a simulated system may have a lot of deviations, right? So in order to ensure that this is not that problematic, you can actually do a deployment of RL algorithm also onto the onto the hardware, so as to ensure that that fine tuning can actually be happening. This time, because we have already trained policy on a simulated environment, we know that our real life hardware is not going to break down or destroy itself, but it may have little inaccuracies which can be solved using the RL algorithm. Okay. Now you can deploy, because these policies are nothing but deep learning networks. These can be deployed on multiple of different hardwares, and you can directly use different coder products that MATLAB has to directly convert all these models into codes that are used by these different library codes. Okay, like you can put it into NVIDIA GPUs, or you can develop CUDA codes and then put it up. You can put it on ARM devices, etc. And if you have some networks, let's assume in some other environment, for example, Python or like TensorFlow, PyTorch, etc. Or you can actually import it into MATLAB if you believe MATLAB is something that makes it easy for you to work with. And we don't want you to lose out on any work. You can import it onto MATLAB and you can easily work with that. And you can also co-execute with Python if you have some codes in Python and that you want to work with us. And if you have any requirement in this direction, please feel free to let us know. We would be more than happy to work with you on that. And just to kind of put synonymity in this. So for a controller, these are the keywords which are mapping directly to these different aspects in reinforcement learning. Like the major one is controller is similar to the policy that we have in reinforcement learning. Okay, great. And This was a quiz, but given the time, I'll just quickly show you. So the whole thing is reinforcement learning has a higher control capability, so it can work for complex systems and for vivid systems, even systems where, for PIDs may not be working or MPC may not be working, you can actually work it. But the caveat is you have computational cost, which is high, and also the deployment cost become medium because PID does not have much of a deployment cost, so it doesn't take much. But reinforcement learning have a little high compared to PID, but very much low considering model predictive control. So the whole thing is you will have to decide on what is the kind of problem. If it is complicated enough and difficult enough to work with PID or MPC, RL may be something that you can take a look at, right? Great. So these are a couple of other things you can actually take a look at when you are deciding on whether you have to use reinforcement learning or not. And I think non-linear environments are most common in real world, and RL will be a great fit to that. Some other application areas of RL, we have shown you water tank level control robot. This is something where there is a prosthetic that is being working. This is a robot which is, if I'm not wrong, Boston Robotics or some company is actually having a robot similar to this, and they use products and reinforcement learning to kind of come up with this walking model. This is automated driving scenario. This scenario itself can actually be simulated in this animated environment using Simulink. So if you are interested in any of these application areas or any other application area, please feel free to contact me or Amit. We'll be more than happy to work it out with you. And this is an example or a story that I wanted to share with you, wherein Vitesco was using a reinforcement learning and Simulink model to incorporate these reinforcement learning models and prototype and generate their solutions. And they found a lot of value in quickly being able to prototype and generate the reinforcement learning agents that they required. So if you find this to be useful, please do let us know. You can find a lot of information and the presentation that they did in our one of the conferences also present on the website. I've linked it up over here, so you can take a look at it when you explore the slide. So these are a couple of reference examples that we have. In case any of these sound useful or similar to what you want to work with, you can get started with this, so you don't have to worry about building things from scratch. So these are some pros and cons of reinforcement learning. I'm just going to say one of the most important cons is the large number of design parameters, but there are more pros which outweighs the cons in this case if you have a very non-linear and complex system. So these cons can actually be quite elevated by using Matlab and Simulink because you can reuse existing codes and models. You can use simulation for getting more data, and you can also simulate extreme situations so that performance is at least somewhat safer compared to what it would be if you are only focusing on the limited amount of data. And you can always run simulations in parallel or GPU or cluster, so it becomes a little bit more faster so that if you have more data or sample points, you can still work with. And you can create a lot of design parameters or reduce a lot of design parameters by having iterative tuning. You can read a lot of examples on this as well. So thank you everyone for listening. I know we have jumped our time by half an hour. So sorry for that, but I hope this was useful. So this is Dhruv Chandel, who is also working in area of reinforcement learning and robotics. So if you have anything with respect to robotics as well, you can contact Dr. Dhruv also. He's unfortunately not able to join us today, but I believe he would be able to join us tomorrow if possible. Otherwise, you can reach out to him in case robotics is also there. And for getting started, I believe you can always go through these courses at matlabacademy.mathworks.com. These are free for everyone. You just have to create a MathWorks account. And if you have an official email ID, please try that, because if your institution has a license, it will automatically be linked to your email ID. And you can, for getting started with MATLAB, you can always do MATLAB on ramp and Simulink on ramp for Simulink. So you have reinforcement learning on-ramp focused on reinforcement learning as well. But I always suggest going sequentially from MATLAB to Simulink to deep learning, then reinforcement learning, because it will give you a little bit more hands-on understanding of how different things work, and you can then scale it up pretty easily. So whole thing is this may require you 8 hours in total to complete all of this, 8 to 10 hours. And with that, you will be in a very good position to use reinforcement learning for your area of application, right? So thank you, everyone. So I will stay here for 5 to 10 more minutes in case of any questions. And if you want to connect with us at any point of time, please feel free to contact us on these email IDs. So for the moment, if there are any questions, please feel free to drop it in. I will stop sharing my entire screen and probably start sharing PowerPoint so that everyone is able to see the email IDs. Please do let me know if there are any questions. And thank you for sticking by us this long. I know it's a little late and you had a very long day, but thank you so much. It means a lot. So
Thank you, Akhil sir. I
thank you,
think
sir.
there is no questions. Everyone is, I think, happy, and everyone is saying about thank you.
Great. Thank you so much.
So thank you very much, Akhilji, for sharing your valuable knowledge to our participants. I think everyone is so happy, so we are very much glad that you are, shared your knowledge. So, dear participants, I think with this we can say thanks to our expert. And tomorrow again we're going to meet with another experts, Amit ji. We're going to discuss more in detail with the theory and practicals. Is there any questions you can raise?
Right,
So
sir.
with this,
I'll stay for 5 more minutes. If there are any questions, please do let us know. And I'll be sharing a feedback form for everyone. So do fill it if possible. And it would be really helpful for me to connect with you and also to understand what your requirements are.
quiz 2 will be available in the canvas 9 o'clock. So don't worry. Your quiz 2 will be available at sharp 9 o'clock. So there is a feedback form. Please try to fill that feedback form. Okay, please log into the canvas, and as Akhilji is also trying to share the feedback. Sir, you please continue. Maybe
No problem, sir. Please go ahead.
no. They actually today they have a quiz exam, so they're asking about some quiz exam. So the things will be available at 9 o'clock. Please check the canvas.
Meanwhile, please, any questions, please put it up. I'll be sharing the feedback form in 2 minutes. Amit, do let me know if there are any questions.
There isn't anything that we have not addressed as far as I can say. People in the audience, if there is anything you think we have not addressed and we may have missed, please do um, repost the questions again just so that we address them. So there's one that just came up about, can you please share reinforcement learning in autonomous vehicles research?
Yep, definitely. Probably you can drop a mail to us and we can have a discussion with you on this. Does that sound better?
Yeah, we have several links to share on that particular topic. If you can reach out to us, our emails are on your screen, and so if you can reach out, we'll give you more specific details.
Great. Amit, I'll be sharing the feedback form now.
Yep.
I hope everyone is able to see the feedback form that I've put up in the chat window. Please share your feedbacks in that form. It is really helpful, and we will be able to connect with you in case there are any requirements from your end regarding any support or any research related or any other queries. We would be more than happy to work with you on that.
Akhil, there's a question that came up. If I want a network environment to be implemented in RL. In Python, there is the OpenAI gem with NS3. Can we create environment of NS3 to be interfaced with Matlab? I am not entirely aware of this myself. Are you?
I'm sorry. Is there is it there in the chat window or somewhere else?
Yeah, no, it's sent privately to me. Let me just send it to all the panelists.
Right. I'm sorry, I did not get that.
Yeah, I
Oh,
just
I
sent
got
it
it.
in the all panelists. We could take it offline if it's involved. You can reach out to us. We could probably.
Right. So if NS3 has a potential COM port or a interoperability with MATLAB listed in their web page, then I think you can get the environment from NS3. But you will have to kind of import it into Simulink to work with because the agent actually is quite integrated with the Simulink portion. Otherwise, you don't even have to use Simulink. You can bypass it and you can directly use MATLAB based agent for that. It is fairly possible, but it will be very slow. Let me let you know that. Because if it is using a COM port connection, the data transmission is not that great. So it may slow down the process. But unless and until NS3 has a native integration with MATLAB, I think you can directly use it. I hope that answers the question. Though please contact us separately, and we can actually try to see if there is something we can do to alleviate your challenges. So I see a couple of responses coming in. Please everyone add in your feedback. It is very important. I hope you have the link to the feedback. I'm just posting it once again so that you can drop in. Amit, I hope that answers the question that you had.
If not, please reach out to us on email and we can share more details. The feedback link has been posted in the chat. I can post it again.
Yep. It's posted in the chat for everyone. I have done it again. Does that work, Amit?
Yep, I opened it.
Great. Great then. So if there are no more questions, we will take we will take the leave. And thank you so much everyone for participating. Please do ensure that you fill in the feedback form before leaving. And if there is any questions or queries that you believe is still left to answer, please feel free to contact us via email, and we will try our best to find a solution to that query together. And we will be sharing all the presentation and demos via the email that we get, email addresses that you would be putting out in the feedback form. And I'll also connect with Professor to get a list of participants so that, if I've missed out, if somebody have missed out the feedback form, they still don't miss out on the, material. I hope that sounds okay to everyone.
Yeah, Akhil, I'm also trying to add your feedback form in our canvas so that they can fill.
Great. Thank you so much, sir.
Other people
That,
also can fill.
right.
Just know
That'd
I'm
be really helpful. Uh, Vishwajit, I'm not sure what your question is. Uh, it- are you referring to this feedback form somewhere? Maybe I can just drop it in again. Can you try this one if there are any troubles there? Right. So okay. Not
Yeah,
sure
dear
why.
participants, all the Matlab feedback form is also available in Canvas. So please fill that feedback form also for today's lecture.
Right.
Or also another feedback form will be that is also we will make it available in the Canvas also.
Right. Thank you so much, sir. So I think we'll take our leave now. It's been quite some time. And
Sure.
thank you everyone for sticking by us. And thank you, sir, for enabling us to do this.
Thank you, sir. Thanks for your time and valuable content sharing. Thank you very much.
Thank you, Professor.
Thank you,
And
Amit ji,
we'll
and
see you
thank you.
all tomorrow.
Yeah, sure, sir. Tomorrow will again.
Yes.
Tomorrow it's a long time for you, 4 hours.
Yes.
Yeah. Okay. Thank you. Thank you once again. Thanks to all the participants.
Thank
Right.
you.
We'll
Good
meet
night,
again.
everyone. Have a great day.
Thank you very much.